British Columbia. My name is Anisha Dhoot, and my mentor was Dr. Heather Trajano. So this is going to be the structure of my presentation. First, I'm going to give some background information on my mentor and me. Then I'm going to talk about the motivation for my project. After that, I'm going to give an introduction to my project. Then I'm going to talk about the methods I use to calculate the annual production of bio-oil. I'm also going to talk about the benefits of using microwave catalytic pyrolysis. Lastly, I'm going to give my acknowledgements. So here's some background information on me and my mentor. My mentor's name is Dr. Heather Trajano. She is an associate professor at the University of British Columbia in the Department of Chemical and Biological Engineering. Some of her research interests include converting British Columbia's biomass into chemicals, materials, and pharmaceuticals. My name is Anisha Dhoot. I'm a rising sophomore, and some of my research interests include global warming, climate change, and sustainability. So the motivation behind my project is biosolids and plastic waste, which is produced from wastewater. There are three different applications to convert it into bio-oil or fuel. The first way is land application. This can be used for agriculture, but it can be contaminated with heavy metals and pharmaceuticals. So it isn't the best method. The second way is thermochemical recycling. This has a high ash content and a low heating value. To have effective fuel, you want to have a higher heating value. Therefore, it is not the best application. Microwave catalytic pyrolysis is one form of thermochemical recycling. It produces low carbon emissions and sustainable bio-oil. So this is an introduction to my project. Basically, biomass, which consists of biosolids, plastic waste, sludge, and etc., can be converted into bio-oil with three different methods. The first one is combustion, which converts it to energy and heat. The second one is thermochemical processing. There are four types of thermochemical processing, which include torrefaction, pyrolysis, which is what my project is about, hydrothermal, and gasification. The third method is biochemical processing. There's two ways to do this. The first one is anaerobic digestion, which works in the absence of oxygen. This way converts the biomass into biogas and methane. The second way is fermentation, which works with oxygen. This way converts biomass into bioethanol. Biosolids are nutrient-rich organic materials derived from the treatment of sewage sludge. These solids undergo the processes of digestion, stabilization, and dewatering to reduce pathogens and odors, making them safe for beneficial use. However, biosolids can be tainted with heavy metals and pharmaceuticals, thereby limiting their reuse and application on land. Pyrolysis is the anaerobic conversion of biomass into liquid bio-oil, solid char, and non-condensable gases in the absence of oxygen. The interest of this project is microwave catalytic pyrolysis, also known as MCP. MCP uses microwave radiation to heat feedstock in the presence of a catalyst, causing it to decompose into simpler chemical compounds. This technique enhances the efficiency of pyrolysis process. So this slide shows the process of how I did all my research. First, I researched the amount of biosolids and plastics generated annually in Metro Vancouver. Then I did the same for Portland, Oregon. After that, I researched the typical microwave catalytic pyrolysis yields. Lastly, I calculated the potential amount of bio-oil produced in British Columbia and Portland annually. So here are my calculations. Table 1 presents the annual production of biosolids and waste plastic in Portland, Oregon, Metro Vancouver. Annual waste plastic for Metro Vancouver was not found. The annual waste plastic for Portland, Oregon was found on the Environmental Protection Agency website, but it might not be a precise representation of the city's annual plastic production. I also used this equation to calculate the amount of bio-oil produced annually. Table 2 represents the annual production of bio-oil based on annual biosolids mass and assumed pyrolysis yields. These calculations provided us with a range of potential bio-oil outputs for both Metro Vancouver and Portland. By establishing this range, we were able to estimate the contribution of each region to sustainable energy production through bio-oil, while also highlighting the potential variability based on process efficiency and feedstock composition. So microwave catalytic pyrolysis has shown a considerable promise in reducing CO2 emissions, which is a critical factor in addressing climate change. By converting biosolids and municipal solid waste into bio-oil, the process offers a cleaner burning alternative to traditional fossil fuels. Unlike conventional fossil fuel combustion, which releases significant amounts of CO2 into the atmosphere, the use of bio-oil derived from MCP can significantly lower greenhouse gas emissions, and this reduction in CO2 emissions underscores the environmental benefits of MCP, not only as waste-to-energy solution, but also as a key component in transitioning to a more sustainable and low-carbon energy system. The findings from our analysis further emphasize the role of MCP in mitigating the impact of fossil fuel consumption, positioning it as a viable and environmentally friendly alternative in the energy landscape. As biofuels have the potential of up to 75% lower carbon emissions compared to conventional gasoline, the environmental benefits are substantial. The economic benefits of adopting MCP on a larger scale cannot be overlooked. And the production of bio-oil from biosolids not only provides a renewable energy source, but also presents new avenues for economic growth. And finally, I'd like to thank Talaria Summer Institute and my mentor for this amazing opportunity and for guiding me through this entire process. Thank you.